Hi, welcome. In this session, we will continue with the discussion on how to apply Laplace transform to circuits. Okay, let's start. So let's consider one more problem. Now, this is an example from Alexander Sadiko's book, and it's example number 16 point. So this is example 16.2 from. Okay, let me draw the circuit first. We have a resistor connected like this. And then we have a capacitor connected like this. Then we have a current source connected like this. Okay, so we have a voltage source. Okay, so this is our voltage source, 10 e to the power of minus u of t volts. Then we have a 10 ohm resistor. Then we have one more 10 ohm resistor here. We have 0.1 farad capacitor here. And we have 2 delta T current source here. And our goal is to find V naught of T voltage across this capacitor. And we are given the initial value of this voltage, means the initial voltage stored in the capacitor is given to us, and that's equal to 5 volts. So what we'll do in order to solve this, in order to find V naught of T, means the voltage across this capacitor, we'll replace it by this equivalent. There's Laplace transform version. So we know the Laplace transform version of 10 e to the power of minus 10 t u of t is simply 10 divided by s plus 1. Now 10 ohm will be replaced by 10. Similarly, 10 ohm will be replaced by 10. And 2 delta t, we know the Laplace transform of delta t is 1. So this current source will be simply replaced by 2. And then we have this capacitor. Now, which model will draw for this? Now we can use, because this has some initial voltage stored, we can either use B or C. Yeah. Now, whatever will give us this voltage across the capacitor, very easy. Now, if you look at this C will give you the very easy solution of this voltage across this capacitor. So what we'll do, we'll replace our capacitor by this model this time. Okay, we'll replace it by 1 by SC and in series with a current source that has value C times V naught. V naught is 5 volts, C is 0.1, so it will be 0.5 amperes. Okay, so let's draw the equivalent model out this. So we have a resistor, and then we have one more resistor here. Then we'll replace a capacitor by this parallel model, that is the C here, this one. So we'll replace it by 1 by SC and a current source. Then we have a current source that is 2 delta T, that is here. And we have a voltage source that's connected here. So let me write the equivalent Laplace transform of these. So first we'll write 10 u of e to the power of minus t. The Laplace transform is 10 divided by s plus 1. Equivalent Laplace transform of this is 10 divided by s. Equivalent Laplace transform of 10 ohm is 10. 10 ohm is again 10. Now 1 by SC, it is 1 by SC. C is 0.1, so it will be 1 by 0.1 SC. So that will be 10 divided by S. Okay. Then we have the CV naught. C is 0.1. and V naught is 5, so that will be 0.5. 0.5 is 1 by 2, so this is 1 by 2 amperes. Then we have one more current source that is given to us. Its value is 2. 2 delta t. Delta t has equivalent Laplace transform. Then we have voltage V naught of t. We can write it as V naught of S. Okay, so we can write this as V naught of S. Okay, now this voltage V naught of S is across this capacitor or this impedance now 10 divided by S. You can also write it this voltage is actually here because we'll assume that this is the reference node. Okay, so now in order to find V naught of S, which circuit analysis technique will be very easy to use here. If you concentrate on this diagram, you will see the nodal analysis method will be very easy. So if we apply nodal analysis to this will give us V naught of S very easily because our goal is to find V naught of T. So we'll find first V naught of S. In order to find V naught of S, we'll apply nodal analysis. So let's apply nodal analysis to this here. So how many branches are there? 1, 2, 3, 4. 1, 2, 3, 4, 5. So 5 branches are connected to this node. So we'll sum 5 currents and put those currents, sum those currents equal to 0. So applying nodal analysis here. Nodal analysis means apply KCL at this node and sum the 5 branch currents equal to 0. That is the nodal analysis. Okay. So what's the current flowing this through 10 ohm resistor? Now on this side we have V naught of S. On this side we have 10 divided by S. So this is an impedance. So the volt current flowing in this 10 ohm will be V naught of S minus 10 divided by S plus 1. This is the voltage on this side. So voltage on left hand side is 10 divided by S plus 1 and voltage on this side is V naught of S. So we'll write it like this divided by 10. Voltage divided by impedance is current. We know voltage is equal to current multiplied by impedance. So current will be equal to the voltage drop divided by the impedance. Now on this we have voltage V naught of S minus 10 divided by S plus 1 and impedance is 10. So this is the current. Now in the second branch, we'll assume the current is leaving. So this is V naught of S minus 0 divided by 10. So this 0 comes from that this node is at ground. This is the reference node. Plus, then we have one more impedance, V naught of S minus 0 divided by 10 by S. Impedance of this branch is 10 by S. Then we have two currents. These are entering. So we have assumed these 3 currents are leaving. So the 2 currents are entering. So we'll say 1 by 2 plus 2. So sum of the currents leaving is equal to the sum of the currents entering. That is called the KCL. So this is the KCL here. Now if we simplify this a little bit, what we'll get? We'll write V naught on one side and the constant terms we'll write on the other side. So we'll have V naught by 10 minus 10 and 10 will cancel. We'll be left with S plus 1 plus V naught of S by 10 plus we have here S divided by 10 into V naught of S will be equal to, this is 2.5, right? So this will be simply 2.5 on this side. Right now 2 plus 1 by 2 is 2.5. So let's take V naught of S common. So what we'll have? So V naught S, we have 1 by 10 plus 1 by 10. This term, and then we have S divided by 10. Okay, that is this term. And this 1 by S plus 1 will take on the right hand side. So this is 2 points. And now it is minus on left hand side. On right hand side, it will be plus 1. Okay, now what we'll do next? We'll combine the terms. So it will be V naught of S will be equal to, this is 2 by 10. So this will be, let me write it like this. So this is 2 by 10 plus s by 10 will be equal to 2.5 plus 1 by s plus 1. So if we further simplify this, so this is V naught of S into S plus 2 R2 plus S. One and the same thing. S plus 2 R2 plus S is same, divided by 10 equal to 2.5 plus 1 divided by S plus 1. So if we take 10 on S plus 2 divided by 10 on the right hand side, what we'll get? So we'll say 10 once multiplied both this by 10, it will be 25 plus 10. And then we have S plus 1 do a whole divided by S plus. So if we cross multiply this and simplify the terms, it will be 25 into S plus 1 plus 10 divided by S plus 1 and S plus 2. So this is our V naught of S. If you simplify this step here, so we have 10 divided by S plus 1. So if you multiply this, it will be 25 into S plus 1. So you can simplify this further. So V naught of S will be simply equal to 25S plus 25 plus 10. So we can write it as S plus 1, S plus 2 in the denominator. On the numerator side, what we have? V naught of S is simply equal to 25S plus 35 divided by S plus 1, S plus 2. Please check the this simplification step again. Maybe I may have done something wrong. If I have done these steps correctly, yeah. Okay. Now our goal is to find V naught of P. So what we'll do, we'll use this in order to apply inverse Laplace transform, we'll apply partial fraction expansion. So we'll say V naught of S, that's equal to 25 S plus 35 divided by S plus 1 plus 2 can be written as we have two factors in the denominator. So we can write it like this. Okay, now our goal is to find A and B. In order to find A and B, what we'll do, we'll multiply both sides by this or simply do the cross multiplication of this equation or terms here. So what we'll get, if we multiply both sides by S plus 1, S plus 2, we'll be left with 25S plus 35 will be equal to A into S plus 2 because S plus 1 term will get cancelled, B into S plus 1. Will be S plus 1 because S plus 2 term will get cancelled. Okay, now in order to find A, what we'll do, we'll make this term equal to 0. So what that I can do by substituting S equal to -1. So it will be minus 25 plus 35 because S is -1. -1 multiplied by 25 is minus 25. A into -1 plus 2, B into 0 because S is -1. So this will be 10 is equal to A into 1. So this implies A is equal to 10. Similarly, in order to find B, what we'll do, we'll put here, put S equal to -2. Now if we substitute S equal to -2, it will be 25 into -2 plus 35. That's equal to A into 0 because S is -2, -2 plus 2 is 0, plus B into -2 plus 1. So what we'll get, -50 plus 35, that's equal to B into -1. -2 plus 1 is -1. So this is -15, I guess, is equal to -B. So B is simply 15. So substituting A and B in this expression here, what we'll get, V of S. So V of S will be simply V naught of S will be simply equal to 10 divided by S plus 1 plus 15 divided by S plus 2, because A is 10, B is 15. So we'll substitute it here. Now we know the inverse Laplace transform of these terms, so we'll write directly. So inverse Laplace transform of V naught of S. So inverse Laplace transform step is, so V naught of S is V naught of t, that's equal to 10 e to the power of minus t u of t, 1 by S plus 1 as Laplace transform e to the power of minus t u of t plus 15 e to the power of minus 2t u of t. Inverse Laplace transform of 1 divided by S plus 2 is e to the power of minus 2t u of t. Now we can take u of t common. Okay, right. V naught of t will be equal to 10 e to the power of minus t plus 15 e to the power of minus 2t u of t. Okay, so this is our answer. This is the voltage across this capacitor that we needed to find here. So this, so our goal, we are given two sources, voltage source and current source, and we are given some initial voltage stored in the capacitor. Our goal was to find the voltage across the capacitor at any time t. So we replaced this circuit by the equivalent Laplace transform model. Then we applied the KCL, right? Our nodal analysis here. There are 5 branches. We summed the 5 currents, and then this simplification here will give us V naught of S. Once we have found V naught of S, we get V naught of T here. This is our answer. So this is how we apply Laplace transform. So the goal is simply to convert the given circuit into the equivalent Laplace transform domain by substituting the appropriate models. Here we replaced 10 e to the power of minus t u of t. We replaced the equivalent model by this. The resistor is replaced by simply 10. This resistor is replaced by 10. Then we replace this capacitor by this second model here. That is called the parallel model of capacitor in Laplace transform. Okay. Then we have a current source here. We replace it by its equivalent this Laplace transform, that is 2 delta t has equivalent Laplace transform 2 because delta t has Laplace transform 1. Then we apply KCL at this node. Okay, we apply KCL at this node. There are 5 branches. We sum the 5 branches. Currents equal to 0, or we say currents entering the node is equal to current leaving the node. Okay, then we simplified this equation. We arrived at this one. Then from this, in order to obtain V naught of t from V naught of S, we use inverse Laplace transform techniques. And finally, we arrived at solution. Okay. Okay, let me stop here.